the Hessian inverse at the k-t direction. So this is our hope. Okay, so this approximation, I mean, as the name suggests, it's approximation, but it was pretty good. So given these two, and this is all normally, so this is normally set as a diagonal matrix, okay, with actually lambda greater than 0. So okay, and then our Quisa-Newton method reads, so for k, which is a number of iterations, okay, we do the following. First, we compute the gradient. So by the way, our goal is to optimize okay, so this f is not a quadratic function anymore. It's just a arbitrary function. So in next lecture, we're gonna learn how to code this, and so we'll use a general example. We'll use some common benchmark in the optimization. Okay. So GK is gradient, and what happens is we update our descent direction using this H matrix. Okay. So D is our descent direction. So this is like a so this is our gradient. And P is our descent direction. Okay. And then we do a line search in this descent direction. So we find alpha sub k such that it is the arg minimum, all right, such that we find the minimum such that alpha is greater than 0. So basically we march along this descent direction, see if we can find the minimum of the function. So we do a line search. So we can view this as the steepest descent. All right. So last step, which is a heart and soul of Quisa-Newton method, is we update H sub k to get hk plus 1. Okay? I mean, so this is the general procedure of Quisa-Newton method. So this is the most important step of Quisa-Newton. And the update rule of Quisa-Newton method relies on this equation. Okay. So we derived in order that, so how to update, this is a kth iteration, and how to update hk to get hk plus 1 is we want our hk plus 1 satisfy this equation. No? Okay. Okay. And why this is the case? Okay. So this is obtained let's briefly recall how we derive this. Okay. So so this is obtained by expand f, Taylor expansion, old friend. So at the kth iterate. Okay. So a lot of cutting edge research in optimization relies on this crucial tool, which is Taylor expansion. If you guys want to do some research in optimization or anything relevant to optimization, so when you read the paper, this formula is being used, I don't know, billions of times. So okay. So if we don't want to add what's left, what we can do is we change this term to CK. All right. Okay. So we change this term to a CK. It is a point. So this one is a point between x and xk. Okay. So now we take gradient of this with respect to x. So we will have this as gradient of f at this point. Okay. This is a constant because this is evaluating f at a point, so this is gone. We take derivative of this term, we'll get gradient of f at xk. Okay, take derivative of this linear term. Then we take gradient of the quadratic term. We'll get this is the Hessian matrix evaluated at some point between x and xk. Okay, multiply with x subtract xk power. Sorry, x subtract xk iterate. Okay, so now we plug in. So now we let this x to be our k plus 1's iterate. Okay. Yes. Question? Something wrong?
I'm just wondering how you can replace in the second line, how you can replace that derivative, like with the gradient of fk, with the gradient, with the Hessian of the, whatever that.
CK? Okay, so the question is how we do this. So if we don't do this, we have to have, so let's recall.
Okay.
1D. Okay. If f is infinitely differentiable, we will have something like this. Taylor series. If we want to stop here, what we can do is we apply intermediate value theorem and change this to. So suppose x is greater than a or x is less than a, whatever, this Kc is between x and I don't know.
So, okay, yeah, so that makes sense for the first line, how, because we wanted to stop there, but then how do you just, when you take the derivative of the first line,
Yeah.
then how do you, why does it just change, because that last term is gonna be
Where did it
constant?
go?
Anyway, like,
Okay,
yeah,
so we can rewrite this equation as,
so I think the last term is confused, but
so we can rewrite this equation as f of x equals c plus
like
b transpose x subtract, I don't know, so let's name this xk still, plus so let's make a change of variable. Let's make a change of variable so that this is y, this is y transpose, this is 1. So gradient y of the same f is, so using what we have learned, so it's going to be qy plus b. Agree? So if we have a gy equals 1/2 y transpose qy plus b transpose y,
yeah, but how, why are we not just replacing it with x? Why are we replacing it with that? Like, I'm just merely asking, like, why are we replacing in your second line, instead of this, the Hessian of xk, no, in the second line, yeah. Why are we replacing xk with the new letter? Why would it not just stay with
because then we have to add the error term. So if we only want to expand the Taylor expansion using two terms, we replace xk with a point between xk and x. This is another constant matrix.
Okay.
You sure? So we take derivative of this. So gradient of f is then, we evaluate this at gradient of evaluate of y equals this, and then matrix product with the Jacobian of y with respect to x. This is an identity matrix. So what we obtain is, so we take derivative with respect to x, okay? So we take gradient of the first equation, we get this one. Yes?
Okay.
So now we have, this is, all right? So this is our Hessian. So now we have the error equation. This is delta g, this is delta x, and what we want is, so what we want is, we want to construct, this is a matrix, okay, so we want to construct something approximates the inverse of this matrix. So then what we can do is, all right, so we let this to be, so we let this guy to be okay, delta gk, which is the change in the gradient. This is the change in x. Okay. Then for the Quisa-Newton, what we want is we want to construct something approximates the inverse of it without really taking inverse. So this is like the mentality of computational math is we want to save computational resources using calculus. So that's like the punchline. Okay. So then what we want is we want hk plus 1 satisfy, because this matrix, we want to approximate the inverse of this matrix, we can multiply the inverse on both sides. But we don't want to exactly compute the inverse of it, so we want to, so this is what we want. So we want to construct something that satisfies this. Okay. So the whole update rule is based on this equation. So this is heart and soul of Quisa-Newton method. So when we learn, after we learn to implement the two simple variants of Quisa-Newton, so we'll learn the state-of-the-art BFGS, and we'll have another equation, which is exactly this equation. Okay. So we not only we approximate the Hessian inverse, but we track Hessian as well. You know, so it gives us a very nice combo. And okay. So now then, it's back the famous SR1 or single rank or SRS. Okay. So basically, we have the rank 1 update. That is, we denote. Okay. So we denote. Right, delta ek as. So we want this equation to be true, all right, to be true. So we compute what we call the residual of this equation for previous k, then we correct hk using the residual. So this is a very, very pervasive idea in applied math. Actually, the famous ResNet, like I said, the residual neural network that has been cited over 100,000 times, is based on this time. That is, we use residual to correct the current iterate. So, okay. All right. We normally will assume this is not 0. Otherwise, this is already satisfied. We already jump to the next iteration. Okay. So if this is 0. So now what happens is, our update rule is hk plus 1 equals hk plus, okay, delta ek, tensor product with itself. And on the bottom is the inner product of delta ek with delta gk. So now let's recall what is this tensor product notation mean. It is just AB transpose. So what happens is, we have an m by 1 matrix, and we have a 1 by m matrix. So what we get is a rank 1 m by m matrix. Okay. Go ahead.
I think last class we just called it EK, not delta EK. Are they the same thing?
I did. Sorry about
Yeah.
that. Okay. Yeah, let's call it
Okay.
EK. Thank you.
But does it still equal like? Yeah. Okay.
Thank you.
Okay.
Thanks. Okay. So, I mean, then we verify last time is satisfied. So this update rule, if hk satisfies the previous iteration's update, this update rule will make hk plus 1 satisfy this equation. Okay. But the drawback of this is, okay, so HK plus 1 may not be a positive definite matrix, even if HK is. Okay. Question? All right, so this is a drawback. So then, today, we're delivering the update, not update, like the fix to this, okay? So, the rank 2 update of Quisa-Newton also known as DFP method. Yeah, I forgot what this D is, but the F is the F in the BFGS lecture. I think this is Paul. So I think Paul is Fletcher's student. But yeah, this guy is pretty good. So it's like the mastermind. But anyway, so the DFP method is okay. The idea is simple. How do we make the update rule satisfy this equation while maintaining the positivity of HK plus 1? Okay. So the idea is the following. So we have the same first term. So the idea is we add a correction to this. Okay. So we add a correction to this term that when we inner product with this, it's going to be gone. But the formula, but after simplification, so I'll provide the simplified form. So after simplification, it is so it's a long formula, but the idea is basically, so the derivation of this is we add, I mean, this may not be positive, so we add an alpha, maybe not alpha, maybe gamma, delta xk, and then we have this delta, and we add this, okay? And we figure out what this gamma is. It turns out the gamma is pretty complicated and we have to do a few manipulations, but overall the formula is like this. Okay. I mean, so if you guys are interested in the derivation is in the Nocido Wright textbook. So, but I'm not gonna. So we're not gonna learn this during our class. But okay, so this is our DFP, and so first is, so let's name this, okay, DFP update rule. So first proposition, is the DFP update rule satisfy the area equation. I mean, let's give this area equation a name. All right. In fact, it's not very difficult to prove. And once you guys see it, it's kind of very intuitive. So we just plug in, okay, the formula to the left side of the area equation. And then we multiply the same thing on the right side of this equation. So we'll find, so let me just copy down this. I mean, it's a long formula. But it's just we multiply each term. Matrix multiplication of each term of this updated rule by this delta, by this change in the gradient. Okay. So then we couldn't help but notice, okay, so we have this formula that is A tensor product with B, then we multiply with B is same thing as A B transpose B. So what we can do is, instead of computing this A B transpose first, we use A times B transpose B. Okay. So this operation has complexity order n squared. So this computation has computational complexity order n. Because this is getting first an n by m matrix, and n by m matrix multiplied with an n by 1 vector. It has complexity order n squared. But this, we first compute the inner product between these two. And this has complexity only order n, and the same thing. So now this becomes a constant, and multiplied with a, of course, it's order n. So the denominator is a number. Okay, otherwise we can't write it in the denominator if it's a matrix. So it's a number, and then it's this tensor product with this, and then matrix multiply with this. So what's happening is, so this term will become HK delta GK, okay, these two inner product. So B transpose V, I mean, using our favorite notation, actually using my favorite notation. If you don't like this, well, it's normal. I mean, so this is the most natural, I mean, notation for Hilbert spaces. But I think some engineering people hate it. Yeah. Sorry if you don't like this notation. So let's rewrite using this notation. What happens is it's HK delta GK comma inner product with delta GK. And somehow this term looked very familiar because it's the same as the denominator. Okay. So they are going to cancel. In general, we are assuming, so it's safe to assume delta GK is not 0, delta XK is not 0. Okay. So what does these two 0 means? It means we have no update. To have an update, we have to have both of them non-zero. Okay. So if we have no difference in the gradient, we stay at where we are, you know? So, I mean, no change in x also. So it's safe to assume both of them are non-zero. The denominator is non-zero. This will cancel with this. Very similar things happen here. So this term is, okay, so this term is delta xk, inner product with delta gk, delta xk, delta gk. All right, so these two cancel. These two cancel. And now if we recollect all the terms on the right, we find the first term cancels with the second, and we're left with the third. If we look at this formula. So, okay. This guy, subtract here. All right. So this is what's left. And this is what's left. So then this implies hk plus 1 delta gk equals delta xk. So with that. So we satisfy the area equation. So I think in the original paper, Fletcher with his student, they wrote. So how they discovered this scheme is they examined the eigenvalue of this updated matrix. Okay, so this is another way of doing research. So if we're dealing with matrices, okay, and we want to improve an algorithm, a very natural method is SVD. Okay, so or find the eigenvalue of the matrix, or examine the eigenvalue of the matrix. So now let's prove the theorem. So let's suppose so xk is not a local minimizer . Suppose xk is not a local minimizer, then, i.e., the gradient at the kth iteration is not zero, then what happens is, then if hk is symmetric, positive definite, or SPE, when DFP rules, the DFP update rule will guarantee that HK plus 1 is SPD as well. If we look at the formula, the symmetry is trivial. Okay. The symmetry is trivial is because so the symmetry, let's first argue symmetry. Symmetry is like trivial. Because if this guy is symmetric, okay, tensor product with itself is a symmetric matrix. So Z tensor product with Z, which equals Z times Z transpose, so which we practiced back in our homework 1. So I mean, linear algebra is always important. So it's symmetric. So what we did is we added two symmetric matrices. So these are numbers. Okay. So we still get a symmetric matrix. The key is we want to show positivity. So so i.e., so what we want to show is it suffices to show. Okay. It suffices to show that if HK is positive, okay, i.e., for any U in R n and U is not 0, HK U is positive. So this is like our induction hypothesis. Okay. Now maybe I don't want to erase this. It's okay. Okay. So we want to show so we want to show then HK plus 1 is positive in the same sense. Okay. All right. To do this, let's prove an updated version of Cauchy-Schwarz inequality. All right. So I think in, I don't know, first week, second week, I forgot. We learned something called Cauchy-Schwarz inequality. I don't know, it's like a fundamental theorem of Hilbert spaces. So it says the following: the inner product of U and V, all right, is less than or equal to U norm, V norm. Okay, and the equality happens. So there is something that is equality is when U is parallel to V, i.e., there exists a T such that U is equal to TV, and this T is a scalar. So we want to prove an updated version. I mean, it's the same. It's the same thing, except, okay, so lemma. So when Q is SPD, and we define use Q norm as the square root of QU U, so QU inner product with U, and Q is symmetric positive definite, okay, then this is a norm, and then we have the Cauchy-Schwarz inequality in the Q inner product. is very straightforward. It actually uses the same proof. So basically what happens is we have, okay, so we compute something like this. All right. We know that this is a square term. It's always positive. Okay, but then we expand it. So if we expand it, we'll get something like this. And after a few expansion, so I'm gonna skip writing everything. So I'm just gonna give us a result. So it's gonna be QUU plus 2T. So here we use the symmetry of here we use symmetry of Q. Okay. And plus T square times QV inner product with V. Okay. So this is a quadratic function of T. Okay. So this is a quadratic function in T. T is a scalar. So T is scalar. Okay. So this term is always, so this we denote as a function of T. So this is a function of T. This inner product is a number. This inner product is a scalar. This inner product is a scalar. So it's like AT plus BT plus C. So the discriminant must be less than or equal to 0 because this thing is always positive. Okay? So it either, for T, if we set this thing to be 0, it either has a repeated real root or complex root. So the discriminant is less than 0, and if we compute the discriminant, okay, discriminant is what? Discriminant is B squared subtract 4 times A times C. So B squared, the B is 2 QUV square, subtract 4 times A VB times C is less than or equal to 0. So we move this to the right, then we take square root and we factor out a 2, so we get this is less than square root of QVB square root of QU inner product with U, which is exactly this. And now the key, so we're actually in the proof, in this proof, what we're going to use, the key is when this is 0, it's U parallel with V. So it's because next is when, okay? So when G of T is 0, so when the discriminant is 0, I mean this thing is 0. When G of T is 0, it's this guy is 0. Okay. I mean this is a norm we proved like a long time ago. So this implies, so G of T is this square function. Okay. So U plus TV is 0, or U equals minus TV. So they are like linearly independent. Two vectors are linearly independent and they must be parallel, i.e. or so U is parallel with V. Okay. So equality only happens when the vector we apply Cauchy-Schwarz inequality, they are parallel, or there exists a constant that that one vector is a constant multiple of the other. So now we're ready to prove this. So let's again, let's consider this inner product. Okay. So we have a huge parenthesis. Yeah, let's do this. Okay. So let's do 1 over. So we factor out the HK delta GK at the bottom, and then we have what happens is we have this matrix that is this guy tensor product with this guy. So this is an m by m matrix. Okay. So this is an m by m matrix, and U inner product with U. Okay. And then sorry, minus. Plus, okay, 1 over delta xk inner product is delta g of k, so we copy the same thing. So we have this is delta xk tensor product with delta xk u inner product with u. Okay. So again, this is an m by m matrix as well. Okay, now we're going to use our homework 1's identity again. So now we're going to use our homework 1's identity. So we have, so either two of these forms are, yes?
Does it say 1 by n or n by n?
You mean here?
Yeah.
Sorry, I think,
N by n.
thank you. So, it doesn't, so each one of the inner product over there is in the form of tensor product with V, and multiply with U and U. Okay. So first, let's simplify this. So we use identity we learned earlier. This is V transpose U, and then U, and this is. So this is. So we can switch for simplicity. So it's U transpose times Z times Z transpose times U, but they're the same thing. I mean, okay, right? So it's either Z transpose times U. Yeah, it's actually both Z transpose times U. And let me just do this. Okay, so this is a number. It can be pulled out. Z transpose times U, then Z inner product with U, but this is Z transpose times U, so it's Z transpose times U squared. So now we're going to apply, okay, now we're going to apply it on the first one. happens is then, so let's denote this term as the first term, okay? This term as the second term, and this term as the third term. Then the second term is what we just apply this formula, and what we will have is minus hk delta gk delta gk, and we apply this thing here, so it's going to be hk delta gk. So this is a vector, okay? So this is a vector. Inner product with u, then square. All right. So now let's look at now let's look at the first term plus the second term. The first term plus the second term is h.
Never mind. It's the same.
Okay. So here we're going to use Cauchy-Schwarz inequality. On this term. So by Cauchy-Schwarz inequality, as well as our assumption, that is, so for Cauchy, I erased it, sorry. So for Cauchy-Schwarz inequality to happen, I mean, this thing must be symmetric, okay? Symmetric. And also this thing must be positive. So this is by our induction hypothesis. So this is true. So which means minus of this is greater than the minus of that. And now we plug it above, okay? So it's this thing, subtract 1 over this, and this minus this thing is greater than that. This will cancel with this, and we're left with this, so it's greater than 0. So it implies this is greater than 0 by below. Yes?
Can you explain the Cauchy-Schwarz line again? I'm confused about where you got each one of the,
Is this good?
where did you get like, where did you get all of those pieces? I guess, I'm just like not following.
So this is by Cauchy-Schwarz inequality. We want to get rid of this. So we have it here, okay? Once we apply Cauchy-Schwarz inequality, this term will cancel with this. We're left with this to match this. So it ends up with this is positive, right? So this is Cauchy-Schwarz inequality. I mean, if we want to rewrite, so we let hk to be q, and we let this to be v. This becomes QUU, QVV, okay. So this is like so to make it even simpler, this is like b squared subtract a squared, and this is like a times b squared. Okay. So this is greater than root 0. Okay. Now we're curious about the third term. Okay. So we want to show the third term is positive as well. Okay. And the third term is here. So what we have here is, so we apply the same. Like the manipulation on the top, we will get, this is nothing but delta xk u square, and then divide delta xk delta gk. For this step, we'll be relying on our Quisa-Newton algorithm we reviewed in the beginning of the class. Okay, so notice the following thing. So the update rule is, so let's first rewrite delta xk as this. Okay. What is the update rule? The update rule is we do a search along dk. So it is alpha k dk. And what is dk? Dk, in generally, it follows a negative gradient direction. So let's continue this identity. So this one is alpha k h sub k minus gk. So we put the minus in front. All right. Let's plug in this, we get negative.
How did you get like third equation is equal to that term?
Let me hear.
No,
The third term?
Yeah.
So this is our third term, right?
Okay.
So this is so third term is z. So we use this identity again. Z tensor product
Oh, I
of
see.
ZU.
Yeah, I got it.
So we'll get the top.
Okay, yeah, sure.
Thank you. Why we're getting a negative number here? So
But
alpha is positive. Say it again.
Well, aren't you gonna end up squaring everything? Well, I guess not the bottom.
Let me see. Okay. So GK. Oh yeah. Sorry. Yeah, it's good. Okay, my bad. Okay. So now this is a square. I mean, this is a. We assume delta xk is not 0. So this is a non-negative quantity. So now let's consider the bottom. So we want to show the bottom is a non-negative quantity. Okay. So what we have is delta xk inner product with delta GK. Okay. So what we have here is minus alpha K HK GK, so this is delta XK, and then delta GK is GK plus 1 subtract GK. Okay. Let's notice an important fact, that is, this one. So this is delta XK. So when doing the line search, whenever we do the line search, so if alpha K equals the arg minimum of alpha is greater than or equal to 0, so if we do this, okay, so this is steepest descent. Okay. So we derived this, I don't know, back in a month ago. What happens is the consecutive iterations gradient are orthogonal to one another. Okay. So in this context, it's actually this one is orthogonal to delta xk. To see this, this is very straightforward to see, because for the alpha k, this is our xk plus 1, okay? So what happens is the gradient of xk plus 1, because alpha is the line search, alpha is like okay? So this can be obtained by here. So we'll have this is gradient at xk plus 1, okay, times chain rule, partial xk plus 1, partial alpha, evaluated at alpha k is 0. Okay? So what happens? This is gk plus 1. And what is this? This is actually equals dk. Okay? All right? dk is what? dk is parallel to delta xk. Because we move along dk, right? So the change in the kth iteration is parallel to this. So this, again, so this is a slightly modification of steepest descent. So this is orthogonal to this. Okay, this is orthogonal to delta xk. So the first term is actually 0. So let's name this term dagger. So the dagger is, this is orthogonal to this, so we're left with minus minus cancels, so we're left with alpha k. Yeah. Okay. So alpha k is non-negative, I mean, because we do a line search. HK is already positive, symmetric, definite, so this is non-negative. Okay. So the rest of the proof is to show so let's keep it here. So then the rest to prove is, so now it suffices to show that 1, 2, 3 cannot be 0 at the same time. Yes.
The part 3 has we only dealt with the bottom. Are we assuming that the top's always, because it's squared? The top's always positive because it's squared?
No, negative. Yeah. Okay. Now we use Cauchy-Schwarz inequality again. So by CS, 1 plus 2. For 1 plus 2, we use Cauchy-Schwarz inequality. So 1 plus 2, if 1 plus 2 is 0, okay. Sorry, 1 plus 2 and 3. Okay. So if 1 plus 2 is 0, it just means U is parallel to, so U is in the direction of delta GK. I mean, this is by Cauchy-Schwarz inequality. It is 0 only when this happens. Now we look at this. Okay. So if U is parallel to delta GK, what it means is, so U equals, so there exists T, that's in R, and moreover we want to assume T is not 0 such that U equals T delta GK, and now we plug in to the, then part 3 equals, so then part 3 equals delta XK times this guy square divided by delta XK delta GK square. We pull out T. Sorry, there is no square. So if we pull out T, so we have this is T squared, and a copy of this will get canceled. Okay. I mean, when T is 0, we kind of already, so it's a trivial case because we don't want our U, so we don't. When T is 0, because U has to be a non-zero vector in order this work. Okay, so T must not be 0. So now we have the third term in this, but we have derived that, where was it? So it's here, right? And we've derived that this guy is this. So this is T square alpha K H sub K GK GK. Okay. And this is strictly positive because by the assumption that GK is not 0. So in the first assumption, we assume xk is not a local minimizer, so the gradient at xk is not 0. Okay? So we've shown that, so now we're done. Okay. So we've shown that if 1 plus 2 is 0, then 3 cannot be 0. So that's it for today. So next lecture, we're going to learn how to implement the DFT method in Python. Okay.
Thank you.
I have a question on the homework. So it's like the one that's finding the section for alpha actually QH, but then and it doesn't say anything. So I don't know if it's wrong.
I heard it was easy.
Okay, thank you.
হ্যালো আমার ভাই, হ্যাঁ ভাইয়া, এই তো ভালো। হ্যাঁ ফোন দিয়েছিলাম আজকে সকালে, বৃষ্টি হইতেছিল তো ওই জন্য বললাম একটু কল দিয়ে দেখি আপনি কি নিয়ে যেতে পারবেন কিনা। আমি ভার্সিটিতে। আপনি কখন বাসায় যাবেন?
This is the fabulous list,
আমি আমার মানে 12:30 আমার 12টার সময় পেন্ট্রি দিয়ে যেতে হবে, তো ওখান থেকে তারপরে আমি বাসা যেতে হবে। কারণ এর জন্য বৃষ্টি পড়লে এর জন্য বলতেছি যে আপনি যদি যখন 12:30 পর যদি ফ্রি থাকেন তাহলে একটু বললেন, আমি কল দেবো না। ওকে ওকে ঠিক আছে।